This is the Theory and Calculations Lab lecture for the Spectrophotometric Determination of Iron lab. So for this lab, we'll be talking about spectrophotometric determination for the first time, and then the next lab, the equilibrium constant lab, will still be using the same ideas, theories, calculations as this one. So this one will be one to refer back to if you're running into problems in future labs. Okay. So the idea of spectrophotometric determination, it's putting a relationship between color and concentration. So when we look at solutions, you can eyeball how strong or how concentrated a solution is based on how dark the color is, or how weak or dilute a solution is based on how light the color is. So, we can do this in the lab, we can do this every day around the house, we can do this whatever, but darker color corresponds with higher concentration when we're talking about, looking at things that absorb in the visible spectrum. So spectrophotometric determination is just putting a mathematical relationship between the amount of light that is absorbed, which is directly proportional to how dark the color that we see, and the concentration. Okay, so the instrument that we use to make these types of measurements is called a spectrophotometer. Okay, and its job is to shine light at a sample and then measure how much of that light gets absorbed. So there's a little picture, and I'm going to recreate that. I don't know how beautiful it's going to be, but I'm going to recreate that picture of kind of the inside working parts of the spectrophotometer, just so you have an idea of what it's doing. Okay, so there's a light bulb. Now, our spectrophotometer that we're using, we're just looking at the visible spectrum. So that light bulb is going to be like a white light bulb, like it does all the wavelengths in a visible spectrum. I'm trying to show different wavelengths of light. That's why all my squiggles are slightly different. So that white light bulb, when it's turned on, it's everything from 400 to 900 nanometers of light are coming out of it all at once. Okay. Now, when we're looking at a specific solution, if it's a certain color, like it's green, okay, it absorbs certain wavelengths of light that we don't see, and then whatever wavelengths of light it does not absorb, it reflects back, and that's what our eyeballs pick up on. So what we want to do is we want to only shine the light at our sample that it will absorb. So we will pick a certain wavelength of light. For this lab, that wavelength is going to be 510 nanometers. So all this light's coming out of the white light bulb. The monochromator's job is to make it just one color. That's literally what that name means. So it's going to take the whole spectrum of light and filter out all of it, but the one you set it at. So for this lab, you're going to set it at 510 nanometers, and then you will, it'll let all of the light, the only light that it lets through, no, this is a horrible wave, but all of the light that comes out the other side is that 510 nanometers. Everything else is blocked. So basically, it's like a filter, is one way to think about it. Okay. So we've selected the wavelength of light that we want, and then we need to put our sample there. Our sample is in a container that's called a cuvette. Okay. That container could be glass or plastic, depending on what type of spectrophotometer that you're using. We have old ones and new ones. You'll see that in the video on how to use the visible spectrophotometer, but the cuvette is the container that it goes in, and the solution is in there. Now what's going to happen is some of this light is going to be absorbed by the solution, and then some of it will not, and so it comes out the other side. So the more light absorbed, the darker the color, the higher the concentration. So we want to measure the intensity of light that we shine at the sample and compared to the intensity of light that does not get absorbed. Okay, so the differences between those are how much it goes into the solution. And so then there's a detector. We don't care how it works in this class. It turns the light into a number, okay, is what's going to happen. And for us, it's going to turn that light into an absorbance value. Absorbance is the thing that the detector is going to then display on the instrument, which is abbreviated by the capital letter A. It is unitless. Its values can be between 0 and 2. Okay, so 0.63 would be an absorbance. 0 would be telling us that none of the light was absorbed, like there was no sample in there that picked up the light at all. Okay. The instrument can also measure in percent transmittance, which is taking the ratio of the amount, the I divided by the I naught times 100. So it's comparing, you know, this amount of light, the amount that didn't get absorbed by the sample, divided by the amount of light we threw at the sample times 100. So 100% transmittance would be that nothing measured at all. So 100% transmittance is the same as 0 absorbance. Okay, and so it's a percentage. So 0 to 100 is what our values are. And then the last unit would just be transmittance, which is the same thing. It's just not in percentage form. It's in decimal form. So the intensity of light divided by the initial intensity of light, and it goes from 0 to 1. So absorbance is the SI unit. It's the one we're going to use. But it's good to be able to convert between them as necessary. So to go from absorbance to transmittance, it would look like this. To go from either way, to go between absorbance and transmittance, it would be the first equation. And to go between absorbance and percent transmittance, it's the second equation. So log base 10 log. So we'd have to, for solving for t or percent t, we've got to do 10 to the power of for this. Okay, so that's an idea of how the instrument operates. Okay. Now, for the lab that we are doing, okay, we're reacting iron. So this specific lab experiment does not directly correspond to one of the chapters in General Chemistry 2. It gets us practiced with a technique that we will then use to apply this technique to equilibrium, which will be the next lab. So for this lab, we're just doing a chemical reaction with iron. Okay, so iron 2 ion. And we're going to react it with O-phenanthroline, which is an organic molecule. That's O, I'm going to write O-phen for O-phenanthroline. And when it reacts, we're going to have the iron will have stuck with the 3 of the O-phenanthralines. Is that the O-phenanthralines are neutral. So at the end, this solution is an orange-red color. This is colorless. And this is colorless. So the instrument cannot measure the iron 2 ion. It cannot measure the O-phenanthroline ion because our instrument only measures visible colors. So things that we can see with our eyes in the visible spectrum. So 400 to 900 nanometers. So we have to be measuring a solution that has a visible color. Visible spectrophotometry cannot measure colorless solutions, but there are such things as ultraviolet spectrophotometry, which uses a light source that lets off UV light, and things can absorb UV light, and we would never know because our eyeballs cannot see in the UV spectrum. Okay, so this is the chemical reaction that we're looking for. And for the most part, the chemical that we care about is actually just the iron that we started with. But we can measure this one, and luckily it's a 1-to-1 mole ratio between those two, so we can deal with that. Okay. So the chemical reaction that's going to happen here, it's actually not, it's going to be between these two, the iron 2 ion and the O-phenanthroline. But we have to add several other chemicals as well to keep the conditions just right. So we need to make sure that the pH is the correct value and that everything stays in the correct form. So we're actually going to be mixing lots of chemicals together with this. But again, the whole point is to measure this orangey, the absorbance of this orangey red solution. So what I haven't talked about yet is that mathematical relationship between what the instrument gives us, the absorbance, and the concentration. Okay, so that mathematical relationship is called Beer's law. It's actually called the Beer-Lambert law, but no one remembers poor Lambert. Okay, so this is the mathematical equation. As we said earlier, capital A stands for absorbance. It is unitless. And for us, it's going to come from the instrument. Okay, and I said this is between absorbance and concentration. Well, C stands for concentration. Now, it can be in whatever units it needs to be in. We've learned lots of concentration units. Molarity is common, but it could be molality. It could be mass percent. Or, like in this lab, it's milligrams of iron per milliliter. It's just some unit of concentration. Okay, B is called the path length. And for us, it's going to be in the unit centimeters. And what B is, if I backtrack here, It's the distance, how wide is the cuvette? The wider the cuvette, it's going to impact the absorbance because then more light has to pass through it. So for us, I don't know why I skipped a slide there, our path length for everybody is going to be 1.00 centimeters. That's the size of all of the cuvettes that we're going to use. Okay. Our little epsilon guy, looks like a squiggly E, is either called the extinction coefficient or the molar absorptivity. I'm going to call it the extinction coefficient because the term molar absorptivity kind of assumes molarity is the unit that we're dealing with. So the extinction coefficient is a constant, kinda. It's a constant that is temperature dependent, reaction dependent, and instrument dependent. So whenever we do spectrophotometric analysis, job number 1 for the lab is figure out what the heck the extinction coefficient is. So it's a constant, and it has units, but the units vary. So a lot like in the kinetics, do you remember how the rate constant, lowercase letter k, its units varied depending on what was necessary, like what was left. That's pretty much what the extinction coefficient's units are as well. But the way its units work, A is going to be unitless. So if we look at A, I need to have no units left. B, so I don't know what the extinction coefficient units are. B is going to be 1 centimeter, so I'm going to write centimeters there. And then C will be in, well, whatever concentration unit we're working with. So for this lab, it's milligrams of iron per milliliter. The extinction coefficient units need to be whatever is necessary to cancel out the rest of the units. Okay, because when I multiply all 3 together, all the units must cancel. So the extinction coefficient units are going to change depending on what the units of B and C are. So you're going to be able to figure out what those are. And I just gave you the units for B and C. So all you need to do is figure out what unit does the extinction coefficient need to have to make sure all of those units are canceled out completely when I multiply them. Okay. So that's the Beer's law. That's what the symbols stand for. So the way we're going to figure out the extinction coefficient, because I said that's job number 1, we got to figure out what the extinction coefficient is, so that way we can use Beer's law to calculate, like, if I don't know the concentration, I need to solve for the concentration. Well, if the extinction coefficient is the thing that I don't know, then I need to make sure I know for sure all the other variables. I need to know the absorbance. Awesome, I stick it in the instrument. The instrument gives me the absorbance, no problem. Path length, hey, I know that, it's 1.00 centimeters. And then concentration. So I need to know the concentration. So that means first part of this lab, part A, is going to be to make standard solutions, which means you're going to be making solutions that you accurately know their concentrations. So you know the C value, you know the B value, and you know the A value. What you're going to be able to do is you're going to make multiple solutions of that and set this up. Oh, I can't. Fine. Absorbance, and then this is going to be concentration. So we're setting this up kind of like y equals mx plus b, where b we're ignoring. So x is going to be concentration, y is going to be absorbance. So m is the slope. Since we know the path length is 1.00, you're going to graph your data where the y equals mx plus b, m is equal to the extinction coefficient. So job number 1 is for us to make standard solutions. We know their concentrations, test them in the instrument, and then take the data of all of those standard solutions and graph them to get the extinction coefficient, which is the same thing as the slope. So you need to use Excel when you're making this graph because we want the slope to be as accurate as possible, and just doodling something on a piece of paper is just crap, and that's not going to work for how we're doing things. Okay. So the way this lab is going to work is the goal of part A is to do this exact thing. Make this graph, get the extinction coefficient. That's part A's goal. In part B, I'm going to give you a solution, or I'm going to give you a solid that contains some iron. And our job is to figure out how much iron. It's an unknown. So we'll be then using that extinction coefficient to do our calculations in part B. So in part A, we solve for extinction coefficient. In part B, we use the extinction coefficient to solve for concentration. So let's look at the calculations within our data table. Okay, so go into the data table for part A. The volume of the standard iron, that's not a calculation that's given to you in the table in the procedure. So you're just recording that volume. Now, be careful. The volumes that are recorded in the table in the procedure are recorded to the correct number of significant figures. So when you copy them forward into your data table, make sure you write them with the correct number of significant figures. So 2.00 is not the same thing as 2. 2.00 has 3 sig figs, so it needs to be written with 3 sig figs, and then you need to do calculations with it using significant figures. Okay. Second column is the concentration of the iron in the solutions that you made, unrounded. Okay, so unrounded means we're not going to round the correct number of sig figs. So what you're doing in this lab is you're doing dilutions. You're using a volumetric pipette to accurately transfer a certain volume of chemical into the volumetric flask and then adding solvent up to the line. It just so happens that you're adding lots of chemicals. But for calculations, we just care about the iron. Okay, so the stock solution of iron is 0.500 milligrams of iron per milliliter. I'm just going to double check to confirm that I'm not thinking weirdness on this. Oh, 0.5. Yep, it's a good thing I double checked. 0.0500. I'm taking that from the procedure. In the table, it says the volume of the 0.0500 milligram per milliliter of iron standard. That's the standard solution, okay? So we're taking that stock solution, we're taking a pipette and we're transferring some of it into a 50 milliliter volumetric flask, and then we're filling it up to the line. Our job is to calculate the molarity, or the concentration of the new dilute solution. So we're doing a dilution. In Gen Chem 1, we learned about dilutions. Okay. The M1V1 equals M2V2 equation is going to be your friend, and we're going to start using it in this lab and not really stop the rest of the semester. So the M1V1 equals M2V2 equation compares the concentration and the volume of the stock solution to the concentration and the volume of the dilute solution that you're making. So for this lab, we're using the stock solution to make this new dilute one that we're going to be testing. We don't know M2. Now in Gen Chem 1, M1 and M2 were molarities, and V1 and V2 were volumes, and the volumes can be in any unit as long as they're the same on both sides, so they cancel out. In Gen Chem 1, we didn't know any concentration unit other than molarity, so M1V1 equals M2V2 can be used for any concentration unit. I need to go see who's... Okay, so for this lab, instead of molarity, it's milligrams of iron per milliliter. So to solve for that concentration of iron unrounded, you're solving for M2. I just wrote down the stock concentration, so that number is M1. The V1 is how many milliliters of that stock concentration are you using to make your solution. So you just wrote that down when you figured out your volume of standard iron column, which comes from the procedure. So V1 is going to be different for every solution, but you already know that information. V2 is the volume of the dilute solution that you're making. So what's the total volume of what you're making in part A? Well, everyone's supposed to be using a 50 milliliter volumetric flask. So V2 for everybody is 50.0 milliliters. So you're solving for M2. You can do these calculations without being in the lab. You have all the information you need to do these. Okay. The absorbance values, the third column there, is going to come from the instrument. So those are data values. Once you have that, the concentration of iron is going to be your x-axis, and your absorbance is going to be your y-axis for the one Excel graph that you're making for this lab. The Excel graph you're making for this lab is for part A. Okay. And again, concentration along the x, absorbance along the y. It better be a straight line. You will have Excel give you the equation of the line. And then in the data table, it says slope of Excel graph unrounded, line, space, line. So the slope of the Excel graph number is coming from whatever value is there in the M spot. And for a lot of people, this number is in like somewhere around 200. It's different for everybody because every instrument's a little bit different. So, but it should be a largish number, like 200, 100, 300, something like that. It shouldn't be a very, very tiny number. So that's where you're going to get the number part. That's the first blank. And then there's a space, and then there's another blank. That second blank is you telling me what the units are for the extinction coefficient, which we discussed here, that the extinction coefficient units are whatever they need to be to cancel out the other units. Okay. And then you have to submit the graph. You can either upload the graph, like save the Excel file and upload it, or you can print it and attach it. That takes care of the calculations for part A. So for part B, this is when you were given an unknown. I guess part B. This is part A. So in part B, you're given an unknown solid. You weigh it directly into a volumetric flask, dilute it. Now that solution is a colorless liquid, so it cannot be put into the instrument because it has to have some sort of color, right? So then we're going to take that as the source of iron and redo the chemical reaction that we did in part A, like add all those chemicals to it, add the ophenanthylene, make it turn that orangey red color, and then test it in the instrument. Now in part B, we do not know the concentration of iron because you used an unknown. So iron concentration, the C value in the Beer's law, is our unknown for this. So you're going to make this solution, use the solid to make a stock solution of unknown, and then use the stock unknown to make 3 identical dilute solutions. But again, you can't calculate the M2 for this because you don't even know the M1. You don't know any concentration information because this is an unknown. I know you know how many grams of unknown there are, but that unknown is not iron, so you do not know its concentration. So you don't know C. But what we can do is the 3 identical solutions are the orangey red color. We can put them in the instrument and measure their absorbance. So the first column in part B is the absorbance value. So you have to get those first. You're going to get them from the instrument. Once you know the absorbance value, okay, you already know the extinction coefficient. That was your slope from part A. That was the point of doing part A, was to get that number. B is the path length. And I've told you that all of our cuvettes are 1.00 centimeters. C is our unknown. So we have this as a data value. So to solve for the concentration of the iron, you're using Beer's law to solve for C. Use the absorbance for dilute solution 1 to solve for its C, the absorbance for dilute solution 2 to solve for its C, and dilute solution 3. The slope from part A is the extinction coefficient for the entire experiment. That was the point of part A. Find the extinction coefficient and then use that number for the rest of your data. That extinction coefficient is correct for that one reaction at one temperature using one instrument. You did all those things. Those things were all true. So that extinction coefficient, that slope, is consistent throughout the entire lab. So you're not using M1V1, M2V2 to get the concentration of iron unrounded. You're using Beer's law. Okay. Then you're going to calculate the average and the standard deviation of the concentration of the 3 solutions. So that takes us through that first part of part B. Now at the bottom, it then gets to the concentration of the unknown iron standard solution, which is like the stock solution. We weren't ever able to test that solution that we made with the solid because it was not orangey red. Okay? It was colorless. We couldn't put it in the instrument. So I'm going to draw a line here just to keep our part A and part B separate. So I want us to figure out the end result is actually how much iron was in that solid. So I'm going to draw us a picture. So we started with solid, right? And we measured that into this is supposed to be a volumetric flask. So I'm going to call this the iron standard unknown. So the solid is the unknown. I use that to make the iron standard solution, but I don't know its concentration. And then I use that to make 3 identical, yep, we're just going to go with that, of the dilute solutions 1, 2, and 3. Okay. Well, at this point, you know the molarity, you know the average molarity of the dilute solutions. You'll have calculated that. You got the solution, the molarity, or not the molarity, sorry, the concentration, the milligrams per milliliter, from Beer's law for solution 1, 2, and 3, and then you calculated the average. We're trying to get all the way back to that solid information because we don't know information. So we need to go from the number that we know here to that. Well, what you did to go from the iron standard unknown was you took 1 milliliter of the iron standard unknown, put it into the 50 milliliter flask, added all the stuff to it, diluted it to the line. So that was a dilution. We know the volumes on both sides by reading the procedure the V2, which is the dilute ones, well, you made 50, not 5, 50.0 milliliters of it. The V1, you were told to measure at 1.00 milliliters of it. And then you know the M2, the dilute solution molarity. It's whatever the average is. So you're able to solve for M1. That would be the concentration of this solution of iron. Again, you didn't know this otherwise because all you knew was how much unknown you put in there, but you don't know how much iron is in that unknown. So that M1, which again isn't really a concentration, it's in milligrams of iron per milliliter. We want to figure out now, to go from here to here, how much iron, how many grams of iron, or milligrams, I guess, were in that unknown. We know how much unknown there was, but we know that there was some iron and some other junk. And only the iron reacted. Well, you will know how many milligrams of iron there were in 1 milliliter. That's what this M1 number tells you. Milligrams of iron in 1 milliliter. So you just need to think, well, how many milliliters were there? Well, 50. So if there were 50 milliliters, and you know that the number of how many milligrams of iron there are in 1 milliliter, you're going to be able to figure out how many milligrams of iron there are in 50 milliliters, which is a little bit of multiplication. So you will be able to solve for milligrams of iron. Okay. That's not a block, that's not a number you have to record, but it's a calculation you have to do to get to our final calculation, which is the percent of iron in the unknown solid. So the percent of iron, what we're going to take is the grams of iron divided by the grams of unknown times 100. Grams of unknown is a data value. It was number 1. It's the first thing you did in the lab. Grams of iron is a calculated value. Down here, notice you had milligrams of iron. Doesn't take a whole lot of math to turn that into grams. So I know I didn't do an example and put actual numbers in here because part of this is I want you to try to work your way through this. Absolutely ask me questions. That's not a problem. But this is an important problem-solving type of lab. Okay. Now there are post-lab questions. Some of them are directly related. Well, all of them are directly related to the lab in some sort of way because this is not directly related to a chapter. So at the end of this lab, you will have 1 Excel graph from part A, 0 Excel graphs from part B. We're not graphing anything in part B. We're just calculating in part B. And then you will answer the post-lab question. So again, the graphs can be uploaded or they can be printed out, whatever makes you happy. So let me know if you have questions about this.